So, yeah, a lot of you, about half of you missed this actually. So it's C4H10O, and that's the formula you should have gotten. And so there's a couple of choices that you can do, but it's saturated, so you know it's single bond. And then you know there's a possibility of, because it's got an oxygen, alcohol, or an ether. If it had a C double bond O to it, then it wouldn't be saturated. So you kind of know alcohol or ether. Those are your options. And no ring. So, oh, it's gonna let me write on it? No, it's not gonna let me write on it. Let me see something. That's fine. So I'll just point at it. So you can see on that is the alcohol, right? Yeah. And then you have 6 that are a doublet, and then you have a multiplet down here of 1, and then you have a doublet of 2. So you have to figure out what structure would give you that. So I'll just draw this on the board. Oh, look at that. Just draw it on the board. There's a couple of possibilities for alcohols with 4 carbons. One is this. Is this the one you guys answered?
Yeah.
Yeah. And the other one is this. And there's also this one that looks like that. So there's actually 3 possibilities for alcohols. The reason I picked alcohol is because this peak around 4.7, 4.8, close to 5. That's an alcohol peak. That's kind of characteristic. It's off by itself. It's around 5 parts per million. The books always say it can range from 2 to 5, but typically you find it from like 4 or 5. That range. So it's an alcohol. It's got to be one of these. And then one of the simple things you can do is you can just actually look to see like how many signals you would expect to find for each one of these. So this would be 1, 2, 3, 4. This would be the furthest shifted because it's next to the oxygen. So this is kind of like in this region here, but then it has 2 neighbors, so you would expect to see it to be as a triplet. The hydrogen on the oxygen, we talked about this in class, doesn't count. It doesn't couple often. So this structure doesn't work or satisfy like the appearance of the doublet that's here. Even though it's 2 hydrogens, it doesn't have the right number of peaks in it. The other option maybe that you might have looked at, this one's also incorrect, because this would have had 9 hydrogens that were equivalent, and then there's no hydrogen here, so it'd be a giant singlet. And you don't have a large singlet anywhere on here, so that one doesn't work either. So then the question is, how do we make this pattern like correlate to that data? And so on your spectrum, the way I like to do it is that there's groupings of peaks. The doublet, and a singlet. I like calling them A, B, C, and D like that. And then it's a little bit easier to correlate like on the structure what the different things are. So for peak A, the one on the far right, this is a doublet with 6. So you could explain that as these. And the reason would be those.
Well, is this the class that I need to grab sauce?
No, but I could use it at home. But it's probably next door maybe.
All right, for sure, man. You guys take it.
Yeah. I make chili and things all the time, right? Good, great. Okay, so this would have been 6 hydrogens, and they have 1 neighbor, right? So that fits for A. It's also the furthest from the most electronegative group, and so you expect to find it around 0.9, and it's right around 1. So that's kind of where you expect to find it. So you expect these to be methyl groups with a single neighbor. These are the methyl groups with a single neighbor. This guy is typically around 1.5, but as you move closer to the oxygen, it's going to shift further from this position. So this is going to be a multiplet of 1. So that's actually peak B. And then you have 2 hydrogens here. They're coupling to 1 hydrogen, so these will be a doublet, 2. And again, because they're on the carbon that's next to the oxygen, you expect them to be around 1 and 0.4, 1.5. But because they're next to this oxygen, you add 2.5 to that. So you're looking closer to 4. So that would be these guys. They integrate correctly and has the right number of peaks in it. And then finally, when you get to this guy, that's the one we talked. That's where we started. That's this one here. It's D. This is C. That help? Clarify? I think the mistake was you guys maybe got the right numbers of carbons almost, or hydrogens on each atom, but then you didn't really look at the coupling patterns as close as you should have, because that kind of eliminates structures. Right? All right, next.
Tess, are you gonna give us reference to where?
Yeah, I'll give you some, initially I'll be giving you some reference data, but I kind of expect that you'll learn these positions. Especially the ones that can be done as offsets. I'll make sure I'm sharing that still. All right. We'll share this guy. This I can write on, I think. Yeah, that works. All right, so this is kind of the outline of the chapter. We're going to look at substitution reactions of alkanes. And primarily, we're looking at halogenation reactions. And we're going to talk about radicals, and there's a lot of regioselectivity that occurs with radical reactions. The stability of radicals basically follows the stability trends of carbocations. And so the more substituted the radical, the more stable it is. And so that's where you expect to find more substitution taking place. And then we're also going to look at something called allylic substitution. If you remember, this is the allylic carbon. The stability of radicals is also increased by having resonance. And so if you form a radical here, there's some interesting resonance patterns that take place here that cause this to be more stable. So at the allylic position, you often get substitution reactions. We'll talk about how you get substitution as opposed to like addition reactions with like HBr. And then we're also going to look at, this is a very important reaction, it's the anti-Markovnikov addition of HBr to an alkene. So if you have something that looks like this, and you do HBr, and you put it in the presence of a peroxide like this, the product you get is this. So it goes opposite of what you expect it to do based on straight addition. And I think the way this was discovered is like when Markovnikov was doing these reactions, he would do the reactions, and sometimes you get the Markovnikov product, the ones you expect. And then every once in a while, he would have these odd products in his product mixture of these anti-Markovnikov additions. And it turns out when they traced it back to what the cause was, it was the presence of peroxides that would build up over time in their solutions. And the last thing that we'll cover in this chapter is polymerization. And Bruce, she doesn't cover a lot of like polymerization reactions, so I've added that in at the end because I think it's important that you guys get familiar with this. Okay, so why are alkanes unreactive? If you do the electrostatic potential maps, for example, this is 2-butene and butane. Alkenes are very reactive because when you look at them, the electron density is on the outside of the molecule, and it's very easy to get to these and pull them off. And so you can do addition reactions to alkenes, whereas you take an alkane and try to do a straight addition reaction to it, nothing's going to happen. All the electron density is trapped between the atoms of these sigma bonds, where here you have a pi bond, and then the pi bond puts the electron, is what puts the electron density on the outside of the molecule. So how do we do this, right? So if you have something really stable, this general principle, how do you get it to react? If you have something that's really stable, right, it's going to be unreactive. Well, that's kind of the idea. You have to have something that's really reactive in order to make it react. So you have to bring something in that's unstable to make things that are stable react. And the way that we do that is we create radicals that have sort of the odd number of electrons that really need an electron for stability, and those are the things that cause alkanes to react. Another way to do it is to add a catalyst, but I don't think there's a catalyst for an alkane reaction. Not that we've covered anyways. All right. So before we get into radical reactions, we have to talk about the two kinds of ways atoms tend to split apart from each other. One is called heterolytic, and that's the one you're familiar with. So when you're doing an SN1 reaction, and so you have a CH3, CH2, CH3 like this, and then you have a halogen here, and it undergoes SN1, you form a carbocation. So this bond breaks and goes to the halogen, and the reason it does that is because the halogen is more electronegative than the carbon, and so it pulls both electrons off. We often call these ionic reactions, so substitution reactions often referred to as ionic reactions because there's ions involved, and this is caused by the heterolytic cleavage pattern. Then there's homolytic cleavage. And homolytic cleavage happens more often when two things have similar electronegativity. So what happens is you add energy, right? So you're going to take energy, and we're going to use either heat or light. So H nu is light or heat. And that causes the bond to break. If the electronegativities are similar to each other, then what ends up happening is one electron goes one way and one goes the other. And it remains neutral, okay? And the result is two different radicals, this R dot and this X dot. We put a single dot, because unlike here where both electrons went in one direction, I had one electron go one way and one electron go the other. And you'll notice this arrow is different than that arrow. Hard to see, like especially from way back there. But Gus, you got your glasses on today. Can you see that? Yeah, nice. So yeah, this is a two-headed arrow. The two barbs indicate two electrons, and one barb indicates one electron. Okay. All right. So alkanes undergo chlorination and bromination, and those are the two most useful types of reaction. Fluorination can be done, but they're super reactive. And so you end up getting basically uncontrolled reactions and halogenation occurring in places that you're not intending it for it to happen. And so we tend to do halogenation with chlorine and bromine. Turns out iodine is not quite reactive enough for halogenation. The iodine carbon bond that would form is fairly weak, and so you don't get enough bang for your buck in order to make the reaction go. So this would be an example of a halogenation reaction. You can use heat or light, right? Heat or light, and you'll get chloromethane and then HCl. And then you can use heat or light and then bromine, and you get bromoethane and HBr. High temperatures or light. So the light doesn't have to be super intense, but it does have to be in sort of the ultraviolet range. So it has to be relatively high energy light. But the halogen reactions all require some sort of heat or light. Kind of the problem with this kind of reaction is that the halogenation can take place multiple times. All right. So how do you keep it, but from for example, from continuing on and reacting with this? And the simple answer is they have an excess of the alkane and a limiting amount of the halogen, and that causes it to be more one-to-one. But one of the problems with all these reactions is multiple additions of halogens. It turns out, in my opinion, those are relatively simple to separate, because as you add more halogens to it, you change the weight a lot, so that boiling points become fairly distinct. Their solubilities are different, stuff like that. All right. So this is the mechanism for monochlorination. So if I have one electron going to the left and one electron going to the right, I get homolytic cleavage because the electronegativities are the same, right? One electron goes each way. You're going to end up with two of these. Now, I'm going to draw them all in on this one, but in the future, I'm going to leave all those other ones off because just too many dots to be drawn. So that's the initiation. And then we have what's called the propagation. Okay, so in the propagation reaction, you have your radical, which is unstable, and it attacks basically the first thing it sees on the alkane. One-headed arrow, and this bond will break like this, and then like this. So what does that give me? That gives me my HCl, right? Because these, one electron from here and one electron from here, I'm going to get HCl, and then I'm going to get an alkane radical that looks like this. And the second step of the propagation, and not every propagation has 2 steps, some have more steps, many more steps, but I'll have the radical CH3. So I'm bringing this down to here. And it's going to split a chlorine. Now it could attack another methyl group, but what are you going to get? You'll just get a methyl group. Yeah, you just keep getting the same thing over and over again. So it could attack another one, but you'll basically, we kind of ignore that step because if you take this and you attack that, you just get this back on one side, so it doesn't really matter. Now, because I'm bringing one electron from here and one electron from here, I form the sigma bond that's between the chlorine and the CH3, and then I get Cl radical again. So what does it mean to propagate? It means to like create yourself again, right? Your propagation. Or create a plant. When you propagate plants, you take a plant and you create a little plant from the plant. So basically this is called propagation because in this process, you recreate the radical that started the whole process. And this will continue on until the chlorines are gone, or the Cl2s are gone, or until all the radicals sort of meet their final end. We call this the termination phase. And in the termination phase, any 2 radicals that are produced in the reaction can recombine to form a product. Okay? And hopefully, there's enough chlorine in the reaction that you get your alkyl halide out, and then at the end, you get the termination reaction. So examples of termination reactions would be, I have Cl, right? It's possible that you just get Cl2 of these going back to Cl2. It's possible that you get 2 CH3s together, all right? And you can also form more of the product at the termination step, but any 2 radicals that are shown in this reaction are available during the end of the reaction.
What happens to the second chlorine radical?
This guy.
That's formed in the initiation.
So you go like this, right? I get one of them's here. This other one could do exactly the same thing. We can just continue on. So even though you're forming 2 of them, like if you really wanted to balance this all the way up, you'd have 2s in front of all these things. It just happens twice. At the end, this guy that's left, if you can't find another one of these, then he comes up back here and forms Cl2 again. Yeah. It's a little messy. Radical reactions are a little messy. There's a lot of little products that end up there. All right, let's look at another one. Yeah, so one of the things I was talking about earlier is if there's a lot of Cl radical that's formed, like the concentration is really high relative to the alkyl halide, then what ends up happening is you can get a lot of dihalogenated compounds, trihalogenated compounds. And so you minimize that just by using a lot of alkanes, so there's not a lot of excess chlorine in the system to do the polychlorinations. All right. So this is a little out of order from the way your book does it, but I like doing it this way because it shows the big difference between bromination and chlorination. If you look at a chlorination reaction and you look at the actual product distributions. It turns out you can calculate these. Like on a calculator, you can calculate what the distributions are going to be. All right. What you find is 56% of the product is the secondary carbon, and 44% of the product is the primary carbon. This is for chlorination, but if you run the exact same reaction with bromination, and you have to use a little bit more energy to make it happen. It's a little bit slower of a reaction. Actually, it's quite a bit slower, but so you heat it up and you make it the same rate, but it's a lot slower. When you do this, 96.5% of it is the secondary, and only 3.5% is the primary of the monohalogenated products. So what this tells us, in a sense, is that chlorination is not as selective about where the chlorination reaction takes place. Right? Secondary versus primary versus tertiary, they're similar in numbers. They will be different, but they're going to be fairly similar in numbers. Halogenation reactions with bromine strongly favor the more substituted carbon. Okay, so it turns out if I had made this a tertiary carbon, it would be like 99% of it would have been the tertiary product. So what does that kind of mean? Well, it means a couple of different things. But one is, if you want a specific product, a lot of times it's halogenation with bromine is better. Because what are you going to do with the alkyl halide? What are you going to do? Elimination reactions, substitution reactions. There's a lot of things that you can do once you have the alkyl halide. If you want a specific alkyl halide, especially the more substituted, you're going to use bromination. But if you wanted this as your product, then you're either going to do this and make it into that, right? Or you're just going to do chlorination and then separate these two apart from each other. So those are kind of your choices. So this is actually indicating that there's something important about the structure of the carbon, the alkyl group, and the determination of what products are made. And it just turns out, that's what I was talking about, the substitution pattern or the stability pattern for radicals is the same as that of carbocations. We're forming radicals in the reaction. The products that get made the fastest are made on the most stable radicals. So I have a tertiary radical versus a secondary radical versus primary versus methyl. Tertiary radicals are the most stable because of electron hyperconjugation, right? Electron donation from the side groups. And as a result, they form the fastest. That's going to be our major product most of the time. Okay? More substituted radicals, a more substituted radical is more stable. Now, it's not a carbocation. It's not as electron deficient. So the difference between like a primary carbocation and a tertiary carbocation in energy is much bigger than for radicals. But it's still there, and it's still really important in determining products. Okay. So I'm going to play this game because all books do this. I thought it's kind of nice to do this. Let's assume, okay, that we're going to make two possible products out of this. One product would be monohalogenation of chloro with the chlorine would end up like this. And the other product would be this. So there's either a primary carbon that you could substitute, and if you substitute them on the right or the left, it doesn't matter, you end up with the same product. So that would be this first product, and then there's a secondary substitution. So one of the things books always ask is, what if it was purely statistics, like stability had nothing to do with it? How much secondary product would you expect, and how much primary product would you expect? And they like to use chlorobutane because when you count these up, how many hydrogens are on chlorobutane or on butane? There's 10. Okay? 4 carbons, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many secondary hydrogens are there?
2, 4.
4, right? You're thinking about carbons. Yeah, there's 4. So like secondary, like if you this product, you'd expect it to be 40% because, right, it's 4 out of the 10. And then of the primaries, you'd expect it to be what?
The other 60.
The 60, right? This is 40, so that'd be 60%. You would expect this to be 60%. But, yeah, see, I accidentally touched the screen. Experimentally, this is 29%. And this is 71%.
That's because it's random with the selected.
Because two things are happening, right? It's random where they're attacking, but it also has to do with the stability of the radical at this point. As the stability of the radical changes the rate at which that reaction happens. And it turns out for radical reactions, right?
It's more stable with secondary.
Yeah.
Secondary.
This is more stable. And this is less stable. So this top reaction is kinetically, it's faster. And this one will be slower. Because you got to make the less stable radical as the intermediate in order for the reaction to take place. Yeah, so they know crazy amounts of information about these reactions. So they actually know exactly how much faster each position is, primary, secondary, and tertiary. I kind of forgot what the next slide is. I kind of like to look at it before I start talking. I tell you. Oh yeah, the orbital thing. This is what I was kind of talking about earlier. In carbocation, right, you have an empty p orbital and it gets a lot of stability by electron donation, but in a radical you have a singularly occupied, and it doesn't get as much stability from electron donation. You get an electron. It turns out there's an electron in an antibonding orbital. This is really what I want to talk about. I talked about that already. I want to talk about this. So when you measure the relative rates at each of the carbons, right, tertiaries are 5 times faster than primaries at room temperature. So chlorination reactions are relatively fast at room temperature, so they're often run at room temperature. So what we're going to do is we're going to calculate the relative percentages of 1 and 2 chlorobutane using this information. Okay, so let me draw butane again. Let me draw it out all the hydrogens. So I have C and then H is like this. Is it okay if I don't draw all the H's and we just put sticks there and assume there's H's, right? That's my butane. So this is how you do the calculation for the percentages. There's 4 secondary carbons. So we're going to go like this, 4 times 3.8. So that's going to be 15.2, I think. Is that right? 4 times 3 is 12. 4 times 8 is 3.8 is 3.2. So 12, yeah, so it's 15.2. So that's 15.2. That's the cumulative rate for all secondaries, okay? And then the cumulative rate for all primaries would be 6 times 1. So that ends up being 6. So if you're thinking about cumulative rate, like for each position and how much faster it goes, right? There's 15.2 for secondary, and there's 6.0 for primaries. So to calculate the percentage of each product, you just calculate the percentage that 15.2 is of the total of these two numbers. If I add these up, that's the total rate, 21.2. I'll take 15.2 and divide it by 21.2. So this is total rate times 100. And then that'll come out to be, calculator please. I actually got my calculator back. You do need a calculator for this part. Oh, there it is. I already pulled it out.
Those are you
Anticipation. Oh, look, you flipped upside down on me. Is it flipping upside down on you guys? There we go.
Yeah.
There we go. Oh, weird.
70.
So 15.2 divided by 21.2, that comes out to 71.7%. And then the remainder is going to be, so this is for the secondary product. For the secondary substitution. And then for the primary substitution, it would be 6.0 over 21.2 times 100. Right. Or you could just take 100 minus 71.7. Now, the reason I'm doing it this way is because if you have like primary, secondary, and tertiary, then you have to add to and subtract. So it's easier just to calculate it. 6 divided by 21.2. That comes out to 28.3%. For the primary product. So that's what we would calculate. What was the actual data? Here. Yeah, 71 and 29. So it's pretty close. So this is based off relative stabilities of the radicals that are formed, how fast the reactions are going as a result of it. Okay. Now, questions on this? Pretty straightforward calculation. All right. Once you have the alkyl halide, you can do all kinds of stuff. So this is just kind of fair warning. You do a lot of substitution reactions, all that stuff from last semester, you still have to remember it. What else could you do besides substitution reactions?
Addition, substitution.
You could do elimination,
Elimination, yeah.
right? And once you do elimination, you could do addition again because you have pi bonds, right? You can do ozonolysis and cleave the double bond.
Yeah.
You can do dihydroxylation, you can form epoxides. I mean, it just like, it explodes, right? And now it starts with alkanes. But just remember all this stuff you learned last semester, right? Is adding on, you make alkyl halide. Once you have the alkyl halide, then it's the same as last semester. So practice synthesis problems. It's kind of my plea to you. Practice the synthesis problems so that you can do this.
By chance, do you have a key on all like major reactions?
They're in your book if there's one.
Oh yeah?
Back in the book, yeah.
Oh, very cool.
I think it lists. I didn't think it listed in the back. It doesn't quite sound like that when you read it, but all right. Now look at bromination, right? Now bromination is not as fast a reaction, so you have to heat it up a little bit. 125 degrees Celsius, that's a little bit, all right? Tertiary is now 1,600 times more reactive than a primary. It means 1,600 times faster. Secondary is, right, 82 times faster than a primary. So when you do a bromination reaction, 98% of the product is here already. It's already secondary. And when you do chlorination, it was much lower, right? It was like 20, 21, 22% or something.
29.
For this guy. So yeah, bromine, and there's a general principle that goes along with this. It's the less reactive a reaction is, generally speaking, the more selective it ends up being. So bromine radical is less reactive and more selective than chlorine radical, but this is a general like truth about chemical reactions. I often compare it to when you're hungry or when you're not hungry, right? So you walk up to your refrigerator and you're not really hungry, and you look inside of it, and that's when you yell, "Dad, there's no food in the refrigerator." But sure enough, there's like fried chicken and there's.
You gotta make it though.
No, sometimes it's all cooked. It's just in there and it's cold, but it's not the thing they wanted. They're being really picky. Well, that's in chemistry terms, that's selective. On the other hand, if you just came home from a camp out and nobody knew how to cook and you've been hiking for a week and you open up your refrigerator, everything looks good. You'll eat raw chicken.
Cheese.
Right? Like you'll eat blocks of cheese and think, man, this is the best cheese I've ever eaten. Or anything that's fresh.
Yeah.
Like after camping, it's like a vegetable. Oh my God, that's the best yeah, anyways. So basically, if you're really hungry and you're super reactive, the first thing you see, you eat it. And that's basically what chlorine and fluorine, that's especially what fluorine does.
Why is bromine less reactive?
Oh, we'll talk about that in a second. That's the next thing. That's a good question. Excellent question.
It's bigger or what? Bigger size?
Hang on.
Think it's stiff arm?
So energy diagrams, I don't know, hang on, do I have it on here? Yeah, I have it, okay. So the energy diagrams for chlorination and the energy diagram for bromination look like this. And this is kind of, I drew it in a chemical drawing program. But the first step in chlorination, the chlorine is smaller and much less stable and much more reactive. And it grabs that hydrogen off and forms a radical. It turns out this first step in chlorination is exothermic. And the general principle in stability and transition state it's called Hammond's postulate. The general principle is the transition state looks like whatever it's closest in energy to. In other words, this transition state looks like the alkane. It's supposed to be the. When you look at bromination, it turns out the first step is endothermic. And as a result, the transition state looks more like the intermediate, looks more like the radical. And the result is that in bromination reactions, the radical nature, the stability of the radical, or the radical's nature determines selectivity, okay? So radical, there we go, stability determines selectivity. Now, because that first step is endothermic, that's why you got to put energy into it. That's why you have to go to higher energy. You have to heat it up. And so that means the transition state looks more like the intermediate. This is why, in general, reactions that are slower tend to be more selective. They're slower because they're first steps, right? The intermediate is more important in what the reaction looks like. Here, the reactant is more important for what the product looks like. Here, the intermediate is. So stability of the intermediate determines product composition. Okay, so.
Okay.
Yeah.
But why is it less reactive?
Yeah. We're getting there. Okay, so chlorine is a less stable, right, radical. Smaller, less able to stabilize that single charge. And what ends up happening is when it makes that first radical from either chlorine attacking the primary carbon or from the secondary carbon or the tertiary carbon, these all end up being exothermic. Okay. Because the chlorine is so unstable. Fluorine, like in terms of energy, is way up here, much more unstable. much, much less selective. It just basically, first thing it encounters in the refrigerator, it eats it. It might be the door handle. So it's all determined by the stability of this guy. Because right, this part is all the same. But the stability gained by the chlorine, by picking up the hydrogen, becoming more stable and not being a radical anymore, is bigger than when the bromine is. That's why you got to boost the bromine up by adding energy to it to make it end. Does that make sense? It's the stability of that radical chlorine being smaller and not being able to stabilize that.
So being smaller and not being able to.
Yeah, just like smaller carbocations are less stable than larger carbocations, the ability or anions, the ability to spread charge out is important, and or orbital size is important in stability. So yeah, this is the step. This is the energy to get to the intermediate. These are all exothermic, these are all endothermic. They still follow the general trend because these intermediates are the same as these intermediates, still follow the general trend of you take it from a primary because this radical is less stable, it's going to be higher in energy than if you take it from a tertiary, which will be lower in energy. It turns out this little energy difference is what causes there to be such a big difference in selectivity. Okay. So one of the other differences between chlorination and bromination is, I just thought maybe I could just bring that tablet with me, but it's hooked up to that projector, so I can't actually bring the tablet with me. Much nicer to lecture looking at the slides with you guys. All right. Chlorination is most useful if all the carbons are equivalent. So like I have like hexane here, cyclohexane. All the carbons are equivalent. If you do chlorination, right, it doesn't matter where the chlorine attacks, they're all going to end up being the same product. But halogenation is like bromination is more useful if there are different carbons on the structure. Because what the bromination will do is will selectively pick where it goes. Now, having said that, right, if you want it out here, right, don't do bromination because it's all going to be over here. Right? If you want it right here, then you might do a bromination and move the double bond through a series of reactions. But yeah, if you're going to try to do something that requires the halogen to be in a specific spot, this is probably the best way to do it when it has a structural difference in the alkane. Okay. When it doesn't have a structural difference, this is typically when you use chlorination.
But you could use bromation for the top one.
Yeah, you could use bromination for this one as well. It would still work. The chlorination's faster. You don't have to heat it.
Yeah.
You shine a light at it. One of my only real introduction to radical reactions actually in practice is I took a class at UC Santa Cruz, and they had this big glass panel, and they filled it up with chlorine gas, and then there was like a butane or something in there, gas inside there. And so chlorine's yellow, so you can see it. So they turn all lights off, and they put some light behind it. You can see this panel of chlorine gas sealed in, and then they took a little laser, and they shot it. And right where they hit it, you could see the radical reaction spreading out as it consumed the chlorine. It was really cool. It's kind of dangerous, probably takes a lot of money, so I've never done it. But I still remember that one demo at Santa Cruz. I'm like, that's like the coolest demo ever. And then I didn't really understand what they were trying to show us until later. I'm like, it was cool to see it, and then you piece it together, and oh, that was the chlorine gas reacting, and then it all got clear, and so there must have been a product in there that we couldn't see. Yeah. So why only chlorination, bromination? Wait, like I said, you can do fluorination. That first step, the delta H for that reaction is negative 31 kilojoules. It's just way too reactive. It goes way too fast, and it's dangerous to do it. It explodes, yeah. In fact, that's what everybody says, reacts violently. What they mean is it explodes. When they discovered Teflon, they were trying to do polymerization reaction. They had fluorine in there. They had to do it inside a steel cylinder that they could screw the caps on the end and run the reaction inside of that. And when they first discovered, I don't know if I told you guys this last night, when they first discovered it, it stuck all over the inside of the reaction vessel, and they couldn't get it out, and they thought, oh, this is a waste. It was a wartime effort trying to develop something. And so they set the Teflon aside till the end of the war, and they came back after the war and said, oh, maybe this is useful, and then that's how we got Teflon. All right. I just thought I'd show you this real quick. One of the things that can happen in ethers, I'm primarily showing you this because one, it's useful in a later chapter, and the other is you're going to be dealing with ethers on Friday in lab. So if you form a radical in a solution with an ether, you can remove the hydrogen next to the oxygen, and that radical then can react with oxygen in the air. Okay? So this is actually O2, but they separated the electron. And it forms what's called a peroxy radical or peroxide radical, which then can propagate, this is the propagation step, create another radical, just like this one, and then form this peroxide. So here's the problem. These are super unstable. They'll form underneath. They used to use glass bottles all the time, and they'll form where the glass stopper meets the bottle, because the air comes in from the outside and the ether is on the inside, and as soon as you turn it, it explodes. So, anyways, we're going to use plastic. Just telling you. And the reason peroxide is so reactive is it turns out this oxygen-oxygen bond is relatively weak. The single bond oxygen bond is relatively weak. All right. So we're going to go over this reaction. This is an important one. This is the anti-Markovnikov reaction of addition of HBr to a double bond. So I have one butene, and I run HBr, and this is the addition reaction you know and love. You have HBr, right? Positive here, negative here, double bond breaks, two-headed arrow, and then you get the intermediate, which looks like this. And then this attacks and forms a product, right? So this is ionic reaction. It's an ionic addition reaction. You form ions in it. And you get 2-bromobutane. And the reason you get this is because the primary carbocation is so much less stable than the secondary carbocation. That's where you're going to form the carbocation. When you do it, peroxide, it's that. The bromine's on the end. Yeah, and this is because in this reaction, what you do is you create bromine as the electrophile. You know, notice here, hydrogen's the electrophile. But when you introduce peroxide to this reaction, what it does is it creates a situation where bromine becomes the electrophile, and you form the more stable radical, which then picks up a hydrogen. Okay? And I'll show you the mechanism, sort of walk you guys through it. So I just drew this one all out. I'm just going to talk it through. In fact, I just stole this one from the book, honestly. So again, we talked about peroxides being relatively unstable. So when you hit it with light or you heat it, you can break that bond. You get this alkoxy radical, which then attacks the HBr.
So is the radicals more stable in the propagation?
Then the what?
Is like the reason why the BR goes to the outside, so the radicals more stable on the propagation, like on the secondary margin?
Oh, you're looking down here?
Yeah.
Oh, yeah, sorry. Yeah. That, yeah, sorry. Yes. All right, so I'm still up here. What are you talking about? Secondary carbon. All right, so the oxygen grabs the hydrogen, and you form this bond. The OH bond is stronger than the OBr bond, so you get this one. And you get the bromine radical. And the bromine radicals, this is all initiation to get a bromine radical. Once the bromine radical forms, it attacks the double bond, the pi bond, because those are the most available electrons in the system. And then you form bromine on the primary, but the secondary carbon now carries the radical because it's more stable. So this radical will pick up a hydrogen from the HBr and then form another bromine radical. And this is the anti-Markovnikov product. Right? H often is the target because the product is more stable because the bond is shorter.
Is there ever a instance when the BR gets the electrical product? Or the instead of getting the hydrogen, it gets the
Well, that's what that is. Straight addition.
yeah.
Yeah. But if you have peroxide present, this is the route that the reaction takes.
Okay, so it wouldn't even pick up the BR at all.
I don't think it does. It might be there, but I don't think it does much if it does. All right. So in the process, all right, if you were to run this without the peroxide, you get a hydride shift because you form a carbocation here, and then you get a hydride shift. So I gotta let somebody in the room. Hello? It's probably Abby. I don't know. Let me see.
It's around the person now.
It's nobody. Oh wait, was it Adam?
Yeah, Adam.
It's Galaxy S10, whoever that is, and welcome. Wait, I don't know if she has her. I have the speaker muted when people come in, so they don't accidentally say things that they're not expecting to. And I also have the video turned off because people will attend lecture online like in their pajamas or less, and so I decided it's probably best to just leave that off. Well, nobody needs to see that. Maybe you guys want to see that. Nobody needs to see it. So that's different. So the peroxide, because you form a secondary radical, it turns out there's no rearrangement from secondary radicals. They're not as unstable as carbocations, and so there's no rearrangement. Stop working. Now there we go. Peroxide effect only occurs with HBr. It turns out if you try to do with HCl, you only get a straight addition reaction, the sort of normal electrophilic addition reaction. The radical with iodine, you get the same kind of thing. The simple reason, this is the simple reason, right? Is that when you look at the steps in the mechanism, for the chlorination, the first step is exothermic, but the second step ends up being endothermic. So that stops the reaction.
And it rearranges.
No, just if you try to do the radical reaction with chlorine, and you try to do the anti-Markovnikov addition with the peroxide, what ends up happening is the first step is exothermic. That is the formation of this. Second step, endothermic.
On the last slide,
That one?
No, the one.
Right, but it doesn't happen when you do it on
Chlorine.
Yeah. If you do it with chlorine or with iodine, you only get straight addition. So you could have just left the peroxide on.
Okay.
The peroxide actually doesn't end up affecting. It may form a radical, but it doesn't end up affecting.
Why does it not affect the?
Yeah, so that's what we're trying to show in this slide. It's as complicated as this can be. And like I said, this is a simple explanation. This first step, exothermic, first step, exothermic, right? That's the formation of the radical from the alkene. This turns out to be an exothermic reaction. So in terms of spontaneity, it's more spontaneous. right? But then the second step ends up being endothermic on this. So what that does is it causes it to require energy, and so that actually stops the reaction. It doesn't continue on to this part and add the chlorine. It turns out it's only for chlorine and like an HBr that's formed here, that these two steps are both exothermic and both spontaneous. Otherwise, it stopped. For iodine, the iodine carbon bond is so weak, these are all, and the first step is endothermic. So that just stops it before it even starts. So yeah, so the only addition reaction that's spontaneous is the one of HBr addition, because both steps end up being exothermic. Okay, so what does the stereochemistry of a radical reaction look like? Racemic mixtures. That's the answer. You get racemic mixtures. If there's one stereocenter that's formed, you get racemic mixtures. And the reason for that is when you form the radical intermediate, so like this guy here, structurally that's sp2, it's flat. And that single electron, right, you would think, like, because it has that radical and it has a hydrogen here, and you would count, like in your eye, you see 4 groups. You would think that could possibly be sp3 because of the 4 groups and be tetrahedral and have some stereochemistry. It turns out it's flat because it turns out this one electron, remember Vesper theory, doesn't have enough repulsion to push everything out of the way. So it ends up being flat, and when you add the group to it, right, to this flat intermediate, it ends up being able to add it from either side, and so it ends up being a pure racemic mixture. And so you end up with a pair of enantiomers. This is true for like all the racemic mixtures we talked about. You end up with a pair of enantiomers. Now, if you had another stereocenter already in the structure, then it would be distereomer. Because you would have a mixture at one, and it would all be one at the other. It doesn't affect the other stereocenters. Right. See what else is there? Yeah, same thing here. You get a new stereocenter. This also, like the radical addition, the anti-Markovnikov addition, also produces racemic mixtures. Again, because the radicals that are present in the solution are flat, basically. So this is sort of to show that that's the case. You have a radical secondary carbon. It's sp2 hybridized, so it's flat. When it attacks a bromine or an HBr, it can either add it from the top or the bottom, and so you get an even mixture of the two products that would form from them. Let's see. Yeah. So this one, you already have a stereocenter, and it undergoes a radical reaction, a radical substitution reaction. When you pull off this hydrogen, the electron that's left, this is sp2 hybridized, it flattens out. And when you do the addition to it after that, it's a racemic mixture. Okay? So when I said, when you do radical reaction, I didn't really think about it when I said it, but when I said when you do a radical reaction, the product is a racemic mixture, it's true for like everything. I just remembered that in my head, so that's all I said. So benzylic and allylic radicals, all right? This is, we were talking about this just a little bit earlier. This would be an allylic radical, just like we've had allylic carbocations. And what did we know to be true about being allylic? What's the benefit of that?
Stabilized?
Stabilized, yeah, it's resonance stabilized. So it turns out allylic radicals and benzylic radicals are both resonance stabilized. They have about the same stability, and when you look at their stability overall in comparison to like primary, secondary, tertiary, right? What we find is that benzylic and allylic radicals are the most stable, and they're more stable than tertiary, secondary, primary, and then the least stable radicals are the vinyl and methyl radicals. So those are the ones that are least likely to form. See what else is there here. I think that's enough. So when you can do a benzylic substitution reaction, when you have a benzylic carbon and a primary methyl group, right? The substitution takes primarily on the benzylic carbon. For allylic carbons, right, you have primarily substitution at the primary carbon because that's the allylic carbon, more stable than the vinyl. These would be the other options. But then you also get this. What do you get this? So this is the allylic addition, but then you end up with this.
Resonance.
No, not resonance.
So it's not shifting the double bond to the right side?
Last semester stuff. Yeah, it's a bromination of a double bond. So it turns out this reaction is really fast. Right?
Oh, I can see the other BR.
Yeah, so you got two BRs on here. So basic, and I put them one top, one bottom because it's the whole anti-addition thing. Right? But yeah, this is the straight bromination of an alkene. So this reaction turns out to always compete with this reaction if there's a lot of bromine present.
So what would be the most product?
It depends on how much bromine you have. If you have really low amounts of bromine, turns out this is the reaction that takes place. But if you put too much bromine in there, then this is the reaction that takes place because it just hits the double bond and then it reacts. Okay? So it turns out there's a way to control the amount of bromine in the solution, but I'm probably going to save that for Monday. Like, how do you make? You can control whether or not you get this as the product or this is the product by controlling the way you introduce the bromine. Okay? And we introduce the bromine in a reaction that produces it as this reaction takes place. So if you can have 0 bromine in the mixture and produce it while the reaction is happening, that's the best way to do it. And so we use this compound called NBS. It looks like this. NBS allows us to control the amount of bromine that's in the solution. This bromine is only formed, Br2 is only formed during the reaction. You don't add it. And then you end up getting bromination in the allylic position. And then you end up with succinamide. This is the product, which you can then convert back to this.
So you said it controls the formation of...
Yeah, it controls the formation, actually, both HBr and Br2.
Of what, the formation or the...
Yeah, to do this reaction, right, you need Br or HBr to do it, and it controls the formation of that. And I'll show you the mechanism. I mean, if you want to look at the mechanism, things like that. I think I'll save it. We got 5 minutes. I'll just save it for next time. And then I'm going to finish this like pretty quick. So make sure you get caught up on all the homework. Like on Monday, there's not that much more left. There's like, these are just all synthesis and then polymerization reactions, and then I'm done. So, all right. Yeah, so I'm done for today. All right, so who's this other participant? Who's participant number 2? It's Galaxy S10. You know, you could give yourself a name.
Yeah, I heard
Here, I unmuted her. Oh, maybe I can't do that. I'm pretty sure it's Abby. Like, that's the only person not here, right?
yeah,
Cool.
No,
All right, so that's it for lecture. I'm going to end the meeting and stop the recording.